Okay, good afternoon. My name is Mathieu Lucquiaud. I'm in the School of Engineering. My research is basically looking at a family of technology called carbon capture and storage. And what I'll do is I'll explain to you where they stand in the context of energy, fossil fuels, and climate change. So unless you were in space or on a different planet at the end of last year, you must be aware that there was a historical agreement on climate change signed in Paris in December 2015. So this is now almost an all-inclusive agreement where all countries have agreed to take action on climate change. Two important outcomes. The first one is that, if you like, the world has agreed to limit the increase in global average temperature to well below 2 degrees. So the important thing is the well below 2 degrees, so that we can avoid the most dangerous effects of climate change. And a second outcome is that we are now looking at having a neutral carbon balance into the atmosphere in the second half of the century. And I'll explain what it is, why we need it, and how we can do that. So why is the carbon neutral balance is important is because we have a carbon budget. So what this figure shows is that there's a direct correlation between the amount of carbon or CO2 that we put into the atmosphere and the amount of climate change that we get. So now that we've agreed on a 2-degree target, we can basically say that this is our carbon budget of the order of well below 1,000 gigaton of carbon into the atmosphere. So climate change is a stock problem, is how much CO2 you put into the atmosphere. If you put too much CO2, you get more climate change that you are aiming for. Where are we now? So this is taken from a very good website developed by the University of Oxford. We have currently emitted around 600,000 600 billion tons of carbon. So we have we've used 60% of our budget and we have 40% left. If we continue at the current rate of emissions, we will eat up our budget in 22 years, in 2038. And if we want not to release the trillionth ton of carbon that will give us 2 degrees of climate change, we need to reduce our emissions at a rate of 2.7% per year. So how can we do that? One view, some people think that we should leave all fossil fuels underground, not use them. So you can ask yourself the question, is it practical, is it feasible, is it ethical, are we actually going to do that? And this has led this view of, we have to leave fossil fuel in the ground, has led some to think that there might be a carbon bubble in financial markets. So we have monetized resources, coal, gas, and oil, into financial market investments. So if we basically decide not to use this fossil fuel, we will basically effectively create another bubble, another financial crisis. If you look at how much proven accessible reserves of fossil fuel we have in the ground. So this is reserves that we can access economically today. We basically have 3 times more than our budget. And of that budget, we've already emitted 60%. So this is how much space we have. This is how much fossil fuels we have. So is it ethical to say that we can't use fossil fuel? Well, we still have 1.3 billion people without access to electricity. And we also have probably another couple of billion with poor access to electricity or very low level of access to energy. So in places like South America, Africa, India, China, and most of Southeast Asia. If you look at how we have actually developed our economies, we've heavily relied on fossil fuels. So this is the amount of CO2 emission that's been emitted on a yearly basis from 1750 to around 2003, 2004. So you see this exponential growth of fossil fuels. And what we have to do is effectively reduce that curve and effectively get to a level that will give us safe amount of climate change. And once we've eaten up our budget, once we've reached the stock of CO2 that we have into the atmosphere, we effectively want to get our emissions to zero, an absolute zero. Now, is it likely to happen? How are we going to do that? So if you look at predictions from the International Energy Agency, there's 2 striking points. So if you look at, for example, renewables here, this is the green bar here, you see that we predict that the amount of renewable that's going to be used in from 2010 to 2035, so in a generation, we are going to double the amount of renewables that we're going to use. And that's a terrific achievement. Now, if you look at the absolute change of energy, you see that the amount of fossil fuels that are going to, the increase in fossil fuel use between 2035 and 2020 in absolute value is twice as much as that of renewables. So we will double renewables by sort of 1,500 million tons of oil equivalent, and we will increase fossil fuel use by 3,000 million tons of oil equivalent. So we have a problem. We are planning to use a lot more fossil fuels than we have space into the atmosphere. Here I'm not thinking about Europe, I'm not thinking about rich countries that can afford to do renewables, I'm thinking about China, India, Africa, and South America. So how can we solve that problem? And that's the research I do. I work on carbon capture and storage, which is effectively this family of technologies that allows you to continue using fossil fuel. So you can, for example, in this example, generate electricity, turn it into a low carbon product, so make low carbon energy, and transform the CO2 into a liquid that you're going to re-inject effectively where it comes from. So you're going to inject that liquid into depleted oil and gas reservoir, where it's going to be geologically stored for thousands, millions of years. And the idea is that it will never enter the atmosphere, it will stay there permanently. So carbon capture and storage can be applied to power generation, and it competes with renewables, nuclear, and other forms of low carbon energy. But it is also the only options that we can use for heavy industry. So steelwork, cement plants, oil refining, we don't have any options to reduce their CO2 emissions apart from incremental improvement in efficiency, but that's not going to take us to where we want to be. We can't make renewable steel. That just doesn't exist. We need the carbon in that process. So CCS is the only option for heavy industry, and it's an option for power generation. I'm not a geologist, but I just wanted to point out to two common misconceptions in carbon capture and storage and address them with you so that you don't walk out of the room with the wrong ideas. So we are looking at geological CO2 storage well below the surface level. So this is a picture at scale of offshore CO2 storage, for example, in the North Sea in the UK. So we're looking at injecting below water level, so 150 meters of water, and below that the sea floor level to 2,000 or 3,000 meters below that sea floor level into reservoirs rocks that are sealed by an impermeable cap rock so that the CO2 stays there. So we're not getting anywhere close to a potable water level. We're going deep underground where we have oil and gas, and we're putting CO2 in there. The other thing is we're not going to create a bubble of CO2 that's going to move and escape. We're going to inject CO2 in the sandstone between the sand grains. So the analogy to that is if you take, for example, if you take a bucket, fill it with sand, and you add water to it, that water sort of disappears in front of your eyes. It goes into the pore space, and this is the same thing with CO2. This is what we're aiming at doing. So we need carbon capture and storage to address our fossil fuel emissions. We're going to increasingly use more and more fossil fuels. And at some stage, we will reach our carbon stock. And after that, we need to get to this carbon neutral balance. This is what the world, if you like, is agreed to do. How are we going to do that? So we are going to need fossil fuels for aviation, things that we can't easily decarbonize. So we have to compensate for that. And if we excess our carbon stock, we also have to remove carbon dioxide from the atmosphere. There's currently two ways, achievable ways where we can do that. The first one is using biomass energy with CCS. And the principle is quite simple. So if you use biomass to make a fuel, for example, biofuel or fuel for electricity, you take CO2 from the atmosphere whilst you grow the biomass. Now, if you use that energy from the biomass and that carbon from the biomass into a process with carbon capture and storage, you then store the CO2 geologically, and in the process, you have removed CO2 from the atmosphere. You're making a carbon negative product, either electricity or fuel. You remove carbon from the atmosphere. And that's great. The problem with biofuels and biomass is that there's potential there, but one of the limiting factors is land use. We just don't have enough space on the planet, we can't plant enough trees to remove as much CO2 as we will need to. And also, biofuels tend, in some instances, or the first generation anyway, tend to compete with food production. So we are limited by the amount of biomass CCS that we can do. We can do a lot, but that will not take us to where we want to be. And the other option in a post-2050 world where we have used our carbon stock is effectively capturing CO2 directly from the air. So you're processing air into a gigantic plant, and you're making CO2 that you're going to geologically store. That's not a magic bullet, okay, but it's available today, and I'll show you how. It's not a possible quick fix, but it's a vital tool for the end game. We will eventually have to actually remove carbon from the atmosphere if we are not able to limit our carbon stock. We will eat up the space in the atmosphere and probably some more. So what does air capture look like? CO2 capture from air. So this is an artist's view from a technology that's been developed in Canada by a company called Carbon Engineering. And you have this series of fans that are effectively processing tons and tons of air and effectively removing the CO2 that's in the air. So taking it from not very much CO2 to very, very low level of CO2. The other one, and that's being developed in Europe, is effectively a niche market that will be useful to roll out the technology. It's actually how we can make zero carbon fuels. And it's currently available. You can basically go to a German manufacturer called Audi, pay a hefty premium, but you technically you can run your car on zero carbon fuel. How do they achieve that? They capture directly CO2 from the air, and then they use renewable hydrogen made from renewable electricity and the hydrolysis of water. They recombine the C in the CO2 with the hydrogen. They make what they call blue crude. So this is a methane effectively with carbon not coming from fossil fuels but from the air that you can then turn into an e-diesel that you run in a car that's probably have a modified engine. So this is the people putting their foot in the door so that we can open this potential rollout of air capture. So I'm going to finish very soon, and before I do that, I just want you to take a few key points home. So this is coming from the International Energy Agency. Without CCS, so carbon capture and storage, the cost to halving our emissions by 2050 will be 40% higher. So this is absolutely necessary that we roll out this technology globally. It's expected to contribute to 17% of the required mitigation that we have to do, and we cannot build a low-carbon economy without CCS and without putting ourselves at a cost-based disadvantage. In the UK, the Department of Energy and Climate Change is effectively saying if we don't have CCS and we want to meet our CO2 reduction target, we are committing ourselves to spending 1% of GDP extra per year. So having CCS save us 1% of GDP per year up to 2050. CCS is already out there. This is the total CO2 capture capacity in the world. So 2016, we are currently capturing and storing geologically about 40 million tons per year, mostly in North America. And this is expected to increase by 50% in the next 5 years. And this is where we need to be in 2050 and beyond. We need to roll out the technology globally. It needs to be deployed in North America, Europe, China, India, Africa, Latin America, everywhere. This is the amount of storage that needs to be done. So, for example, you have 19 gigaton of carbon that needs to be stored in North America in 2050, 12 in Europe, 42 in China. Where are we now? So I told you we are at 40 million tons, so that's a very small number. Okay, that's a very, very tiny fraction of where we need to be. So if we're serious about climate change, we have to make this massive rollout of the technology. In the UK, this is what things may look like. So the UK is actually blessed with a lot of CO2 storage capacity. The UK has about enough storage capacity to store Europe's CO2 for about 100 years. So one opportunity for the UK is effectively to develop its technology, develop its capacity to store CO2 and effectively roll out technology so that we can store CO2 emitted in England and Scotland into the North Sea, but also take the CO2 from countries like Belgium, the Netherlands, Germany, who have a heavy industrial base and don't have the same capacity for CO2 storage. So this is one of the reasons why CCS has been so prominent in the UK, because of that sort of geological capacity. So just to conclude and summarize a few key points. So there are more fossil fuel accessible than we have space in the atmosphere, and it's not safe to leave them in the ground because they will eventually be used and cumulative CO2 emissions matter. CCS makes sure that the carbon doesn't enter the atmosphere some other way. It's proven at scale, and climate change mitigation is a lot more expensive to achieve if we don't have it. The industry has a lot of stop and starts in the UK, but it's progressing in North America and in places like the Middle East. So we really need to get on board in Europe and roll it out. Now, I just wanted to give you a bit of perspective on when you think about environmental technology and addressing these sort of problems. You typically the industry in any industry goes through a series of phases. The first reaction is this is science fiction. We're never going to be able to do it, and this is where CCS was in the 1980s. Then people start realizing that we can actually do it, but they think, oh, it's impossibly expensive and complex. Then phase 3, it's a major investment but necessary, and this is where we are. We think that CCS is expensive, but we will need it. And effectively, the last stage is, it's obviously just a routine part of any process. And we've seen that with other technologies, such as treating acid rains or nitrous oxide from industrial processes or car. And this is where we need to be in the next generation. So within your lifetime, within my lifetime, we need to get to that stage where it becomes a routine part of any process. So I'm just going to conclude with one more point. Is effectively we're expecting to have an industry with an enormous scale that will require many, many skills in engineering. So I'm an engineer, I'm getting involved, but in geology, in physics, social science, business, and law. So effectively, we're looking at thousands of jobs. For people to get involved. We're starting from a very low basis, but it's an absolutely critical problem, and we will need the technology to address climate change. So thank you for your attention, and I think I'll end up on that note.
This production is brought to you by the University of Edinburgh.